All right, so for question 10, right, they want to know, we got this reaction, nitrogen and hydrogen. So we've got one, two, three, four nitrogens. And that means we should have 3 times as much hydrogen. So I should have 12. I've got 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we don't have enough hydrogen. So hydrogen is going to be our limiting reagent because based on the nitrogen, right, we need to have more hydrogen than we do. Because I've got 4 nitrogens. I need 3 times as much hydrogen. So I really need to have 12 hydrogen. I don't have it. So we could just say the hydrogen is our limiting reagent based on that. The molecule is in excess. Well, nitrogen would be in excess because hydrogen limits. And then of the excess molecules remain after the reaction has completed. So enter a number, not a word. So let's see, if we go back and take a look, basically I need to have 3 hydrogens for every nitrogen. So, all right, there's 1. There's 2 that can react, and there's 3 that can react. So I'm going to have 1 nitrogen that's left over when all's said and done. When all the hydrogen's gone, right, 1 hydrogen is left over. Oh, okay, yeah. Question 11 is actually a tough question because you have to find excess, limiting and excess, right? So the maximum number of grams of aluminum oxide that can be made from the reaction with 48 grams of aluminum with 25 grams of iron oxide. Identified limiting and excess reagent. And how many grams of excess reagent? Yeah, there's a lot of work for question 11. Who would assign such a question? All right, we're going to start with the aluminum. All right, I've got 48. Just 1 excess. All right, 48 grams of aluminum. No, not what I wanted. Damn it. All right, aluminum is 26.98 grams for 1 mole. Who got hurt? 48 divided by 26.98. Right, we've got 1.779 moles of aluminum and then 225 grams of iron 3 oxide. Oh. Well, there was someone laying on the field when I looked over. Let's see, molar mass of Fe2O3 is 159.69 grams. All right, 225 divided by 159.69, and I get 1.4 moles of Fe2O3. All right, to find limiting reagent, we need to know how much of each of those are there, how many grams of excess reagent remain after the reaction is completing. So grams of aluminum oxide can be made. All right, so we're going to convert both of these into, for moles of aluminum, moles of iron, into moles of aluminum oxide. And we can kind of see that this is a 1-to-1 ratio, whereas this is a 2-to-1 ratio. So we actually need twice as much aluminum. So probably our aluminum is going to be the limiting reagent, right? So, okay, 2 moles of aluminum, I make 1 mole of aluminum oxide. Whereas here, for 1 mole of the iron 2 oxide, I'm going to make 1 mole of the aluminum oxide. So that's 1-to-1. So I'm going to make 1.409 moles of aluminum oxide. Up here, we divide 1.779 by 2 to see that we can only make 0.8895 moles of aluminum oxide based on that. So we've identified our limiting reagent, right? Our limiting reagent is aluminum, because when all the aluminum's consumed, I can make 0.88 moles of aluminum oxide. Based on the iron 3 oxide, I could make more. So that tells me, right, the iron 3 oxide is in excess. So the limiting reagent, right, the limiting reagent is aluminum. The excess is Fe2O3. And then we got to find 2 things here, right? Grams of aluminum oxide that can be made. So we want to convert this moles into grams. And then we want to find excess reagent. So we'll do question A first. All right. All right, I've got 0.8895 moles. And I know for 1 mole of aluminum oxide, it's 101.96 grams. So I multiply that by 101.96. All right, we get 90.7 grams of aluminum oxide that we can make. And then grams of excess reagent. So we need to say here, let's see. Yeah, so to find grams of excess, we know we've got that much in the reaction. We used that much of it. We're going to use that much of it. So, okay. For D, I've got 1.409 moles. Yeah, that's the molar mass of the aluminum oxide. And then, so we had 1.4 moles of iron 3 oxide. We end up using 0.8895 moles of that. Right, so we can subtract those two. 1.409 minus 0.8895. And we've got about 0.5195 moles of the iron 3 oxide left over. So we need to turn that into mass. So 0.5195 moles of the iron 3 oxide left over. We're going to use the molar mass, right? 101 mole is 159.69 grams. So multiply by 159.69 to see we're going to have about 83 grams left over. I get 82.96 grams, about 83 grams left over for question 11. All right, we'll do two more questions. We'll do 13 and 16, and then we'll call it a night, and then I can do the rest on Tuesday, or we can do some of these again on Tuesday. All right, question 13 is a redox reaction. Identify the oxidize and reduce species as well as the oxidizing and reducing agents. So, right, in this redox reaction, we can assign charges. We can assign a few charges here. All right, so iron 3 oxide, iron is 3 plus, oxygen is 2 minus. So I've got 2 irons at 3 plus, 3 oxygens at 2 minus. Here, 3 carbons at 2 plus each, because I'm going to have 3 oxygens at 2 minus each. And then this iron is 0. And then here I'm going to have 3 carbons, and I will assign, so in carbon dioxide, we break this down. I've got carbon, 2 oxygen. It needs to be neutral, right? So if it's neutral, oxygen's always -2, so that's -4 charge. That means carbon needs to be +4 to balance it out. So I have 6 oxygens at -2. So the oxidized species loses electrons, right? So carbon goes from 2 plus to 4 plus, right? How did it do that? By losing 2 more electrons. So the oxidized species loses electrons, so that's going to be the carbon monoxide. So it gets oxidized. So that makes our reduced species, right? Reduced species gains electrons. So iron goes from 3 plus. It's going to gain 3 electrons to go to iron 0. So that's our Fe2O3. And you don't have to write it in subscripts. Our oxidizing agent gets reduced. So that's the same, Fe2O3, and our reducing agent gets oxidized. So that would be carbon monoxide there. All right, last one, question 16 here. Oh, of course, it's a calorimetry question. Yeah, so we've got 73.1 grams of metal at 115 degrees Celsius. All right, temperature. And we know the heat capacity. So, right, we're going to find Q for the water. Q for the water, the mass of the water, 182.9 grams of water. The specific heat, 4.184 joules, grams, degrees Celsius. And the delta T of the water goes from 19.5 all the way up to 28.7. Nine point two degrees Celsius. All right, is our temperature change. So Q of the water equals 182 times 4.184 times 9.2. Right, the water absorbs 7,500 joules of energy. And that means that the metal lost that energy. So Q for the metal is a negative 7,000 joules of energy. So now we can do Q equals MC delta T for the metal. We know the energy, negative 7,000. We know the mass of the metal is 73.1 grams. We don't know the specific heat. We're looking for that. And we can find the temperature change, right? The temperature change right here would be 115.2 degrees minus 28.7 degrees. So 115.2 minus 28.7, 86.5 degrees Celsius. So we plug that in. And we multiply, divide across, and we get a specific heat for the metal. So let's see, times 73.1. And then 7,000 divided by that. I get a specific heat of about 1.11 joules grams degrees Celsius for question 16.